Hello everyone, welcome you all to the 24th lecture of this NPTEL course where we are discussing standard model of particle physics, and we have so far derived the quantum electrodynamics basically, and in the last lecture we gave you this introduction to the Feynman rules in QED. And today we are basically use those dictionaries or use those building blocks to construct some of the Feynman diagrams for the processes that can be driven by electrodynamic interaction, and then compute some of those matrix elements or amplitudes of those processes. Okay, so this is going to be very exciting class, and let's see to what extent we can go. But before we do anything, let's recapitulate briefly of what we have done or said about quantum electrodynamics. Now you remember that we had this long urge to kind of have the electrons to talk to the photons so that these electromagnetic interactions can occur, and that's what we actually embedded by imposing what you call the local symmetry or the gauge symmetry on the QED Lagrangian, and then all the important ingredients went inside those derivations, like saying that we utilizing the gauge freedom that is there in the photon field, where mu can be replaced by mu plus del mu chi, and on the same time, we can actually replace the the usual partial derivative in the Dirac Lagrangian by a covariant derivative involving the gauge field mu. Then if we make this transformation like psi going to e to the power I alpha x psi, where the parameter now has a spatial dependence, that is precisely what the gauge interaction means, we have been able to show that the full Lagrangian that we wrote for QED was actually able to abide by the local symmetry transformations that we imposed upon it. Okay, and importantly, it essentially gave rise to the interaction between the electron and photon. Then we talked about the processes, the properties of how we can compute a particular process in quantum electrodynamics using some pictorial notations, and what those pictorial notations and corresponding mathematical terminologies that we should write is actually combined into this definition of what is called the Feynman rules for QED, if you remember. So this is what we actually did last time, and the first thing that we already have seen is that the QED produces an interaction term. Okay, so this is the interaction that we essentially have. Basically this predicts an interaction. So if you see this graph, this is the interaction, and we say that we take out the vertex factor from this. So this term was proportional to J mu A mu, where J mu was essentially the current, which was Q into psi bar gamma mu psi, and then we sort of extracted the vertex factor of this QED interaction process by saying that this is something like minus I Q into gamma mu. Okay, so the gamma mu, you see that it was actually here. The Q was the electromagnetic charge, which is the strength with which the electrons couples to photons, or any charged particle, so to say, couples to photons. So this is the electromagnetic charge, and you have a factor of gamma mu in the vertices. Now each graph or each processes that you can see can have one initial state particle, or which you can say an annihilating particle, and the way that you draw is to have this blob, and the line is incoming, and there is an arrow which dictates the fermion flow, spin flow, whatever that you want to say, which is actually parallel with the momentum flow. So first of all, if it's annihilating particle or initial state particle, the momentum should flow towards this vertex which is given by this blob, and similarly if you have a final state particle, the momentum should flow out of this vertex, and once again the spin flow is along the direction of the momentum, and this is given by u bar p. The annihilating particle is defined by up. You remember that you go back to the mode expansion of psi x and psi bar x, and you will be able to understand why this was there. And initial state antiparticle, when you have initial state antiparticle or annihilating antiparticle, the momentum is flowing towards the vertex, but the spin flow or the fermion flow is actually out of it, and this is denoted by V bar of P. And similarly, final state antiparticle, which is momentum is flowing out of the vertex, but the fermion flow is towards the vertex, and so this is given by V of P. These are the spinors that we have already defined while solving the Dirac equations. And then we have photons. photons, we can have initial state photon, which means the photons getting annihilated. That will be represented by epsilon mu p. Once again, you remember that this epsilon mu was introduced to define the polarization states of the photon, and of course there is a Lorentz index mu which is hanging around, which says that it's essentially a vector quantity, right? And similarly, you have a final state photon, which is like photon is going out of the vertex, the momentum is flowing out of the vertex, and it will be denoted by epsilon mu star p. And then we can have the propagators which are flowing between two vertices, like you can have a photon propagator, which we argued that in the Feynman tooth gauge, this is like minus I g mu nu q square plus I epsilon, and this mu denotes the Lorentz index of this particular vertex, this nu denotes the Lorentz index of the other vertex, q is essentially the momentum which is carried by the photon between these two vertices, and this is also called sometimes the internal line. And most often these are not physical particles which are present, this is the one that carries the interaction between these two vertices, but these particles are not physical most of the time. And then you have fermionic propagators, that is also a possible fermionic line, and we argued that once again this can be given by minus I gamma mu q mu plus m by q square minus m square, where once again q is the momentum which is actually being carried away by this fermionic mediator which is mediating between these two vertices. And finally the QED vertex that you have, and we basically know that any process that you can think of will basically constitute of these three things. One are the external particles, the vertex factor which is actually the electromagnetic interaction ke liye, this is the QED vertex factor that you actually have, and then of course it has to be mediated by a propagator, and so that internal line, whether this is photons or fermions, that we don't know, depends on what kind of processes that we are interested in. And when you take the product of 1, 2 and 3, this is going to give you minus of I into m. The way that we have defined the Feynman rules, this will actually give you minus of I m, where m defines the matrix elements or the amplitude of the particular process. Okay. Then we also say that this vertex, I mean this QED vertex, can imply many things, and it essentially depends on the momentum direction. Like it can define electron scattering, it can define E minus E plus annihilation, it can define positron scattering, it can also define electron positron creation. It also depends on how you actually have your momentum arrows assigned out of the vertex or with the fermion lines, right? And then there is a fermion arrow which will actually guide you that whether these are electrons or positrons. If they are aligned, then these are electrons. If they are opposite, then they are positrons. And then on top of that, you can say that there is nothing very specific about electron. You can actually have muons, taus, all those leptons that we studied in our initial class, which are actually there in the nature. Why only leptons? You can have charged quarks also taking part in this electromagnetic interaction, okay, and giving rise to this pair annihilation, pair production and scattering, okay. So these are the interpretation. There is one property which was left actually, which we didn't discuss, which is the point that whenever you have fermions in particular, there is actually one anti-symmetrization which is actually required, particularly when there are more than one underlying amplitudes which contribute to one particular process. So there the prescription is as follows, that include a minus sign between the diagrams that differ only in the interchange of two incoming or outgoing electrons or positrons of an incoming electron with an outgoing positron. So this is what we have to remember, that whenever you can exchange the graphs by these laws, like electrons can be replaced by positrons and so on, without changing the initial and final state of course, then those diagrams will actually have a relative sign when they compute to the or contribute to the total amplitude of the process. One such example we are actually going to do in our tutorial exercise, okay. Now with this dictionary already in place, we can actually now construct some of these processes and look into the corresponding Feynman graphs. So the first example that we will take is traditionally it's called Mott scattering. Whenever you are electron is scattering with a heavier particles, here for example we consider muon to be the one. So we are considering E minus mu minus scattering to E minus mu minus. First of all, let's look into this process and ask this question, that is it a legitimate process? How do I understand that it's a legitimate process? You see, first of all, that electromagnetic charge must be conserved. So you see that initially you have one electron and finally you have one electron. Initially you had one muon, finally you also have one muon. This is a trivial process, so therefore the electromagnetic charges are conserved. That is the first thing. The second thing is that spin, of course these are all fermions, so therefore there is no problem. So initially also you have two fermions, final state you also have two fermions, so this is a legitimate process. The third thing that you must see is actually the flavor, or the families, if you remember. So you have one electron and you have one muon. So electron belongs to the first family of leptons, muon belongs to the second family of leptons. So therefore this electron number, so to say, has to be conserved in the process, and that is nicely conserved in this particular one. So this is a legitimate process which will be primarily mediated by quantum electrodynamics. And let's try to see what is the Feynman diagram that we can construct using the dictionaries that we have developed so far, and find out what will be the amplitude associated with it. Okay. So in order to draw any of processes or the corresponding Feynman graph, the first thing that you should do is to actually draw a rough picture using this kind of a blob as the vertex. I don't know what exactly happens, what kind of exchange that actually occurs here, but let us draw this electron. So the electron, an incoming electron towards this vertex is an electron with the fermion flow towards the vertex, and the momentum, which I defined as P1, is moment flowing towards the vertex. And there is an initial state muon, so which I am also drawing. So the muon by definition is also a particle, so the momentum and the fermion flow is towards the vertex, and then in the final state out of the vertex the momentum flow of an electron P3 and out of the flow momentum of P4 associated with the muon, which is also going out of the vertex, and the fermion flows are all aligned with the momentum flows. Okay. Now let's ask this question, that can I now stitch this graph using the QED vertex that we know of? Now you remember that we actually had a kind of line which is something like this, right? So we said that this is a possible line that I can draw. So where the fermion flow, I do not have a crossing arrow in the fermion flow because this is defining the fermion current. Whether this is electron or positron, that depends on the momentum. But I have a legitimate vertex given by my QED interaction diagram, where I can have a electron scattering having a photon coming out of the vertex. So therefore I can say that I can join these two vertices together into a blob, and from which I can actually have a photon exchanged between the electron and muons. So you see that this is how you can actually legitimize, or rather describe, this unknown vertex which I was drawing here by essentially stitching the electrons with a photon, and similarly the muons can also do. So the way that QED predicts that this is the electrons are actually doing, so you can similarly say that I can replace this E minus by a muon simply, and this is a legitimate process also. But what I cannot do is to actually connect an electron and muon in the same vertex, because that is something which is not allowed by the QED, because you remember the interaction is of the form psi bar gamma mu psi a mu. So I am only to choose if the psi represents, if an electron, then it will be only an electron current. If it is a muon, then only it will be a muon current. So I cannot join an electron and muon here. This will be wrong. If I do an electron and muon and stitch them together with a photon, this is actually not entirely correct. Okay. So therefore this is only one legitimate graph that you can actually have to actually represent this process via QED interaction. Now let's try writing the amplitude of this process, and let's write individually. So what you have, first of all, you have an initial state electron. Now how do I define an initial state electron? You know, I can actually do it via saying that I have a UE P1, right? That's an initial state electron. You go back to the dictionary if you wish, that you have initial state particle, so that is U, and subscript of E essentially defines that it's the U spinor for the electron. So this is UEP1. And then let's talk about that what is there in the vertex factor. The vertex factor will be essentially minus IE gamma mu. Here I denote this electron charge to be E, okay. So that is IE gamma mu, and then you have essentially this part, an outgoing electron, right, which has a momentum P3, say for example. So usually what I will do, that you remember what is an outgoing electron? The final state particle or particle created is defined by U bar P. So therefore this part will essentially have an U bar P. Now for a particular reason, because I have to then evaluate this matrix element, I will write the UE bar P3 first, then IE gamma mu, and then UE P1. So this completes essentially this part of the graph, right, including the vertex factor. So this vertex factor is also included. So this is represented by this. Very good. What about this part? Once again, this is exactly similar to what we have. So you have a final state muon. So you will call that to be U bar mu P4, correct? This is the muon that is being created. Then the vertex factor will be minus IE. Now we will introduce another Lorentz index, let's call it nu. So that vertex factor was defined by this Lorentz index mu, and this vertex factor is defined by another Lorentz index nu. And what I am going to do, that I am going to write this mu and nu here in these two vertices, and that will help me actually to tackle this Lorentz indices later. And then you have an initial state muon, and that will be simply given by U mu of P2. You see all these P naughts have their momentum dependence. So I am actually writing the P4, P2, P1, P3 in the bracket when I am defining these P naughts. So this defines this particular vertex for you. This defines this particular vertex for you. So this is also done. What remains is the propagator. Now, do you remember what was the propagator? The propagator, the photon propagator, was actually minus of I. Now, the Lorentz indices are mu and nu. So, what I am going to do, that I am going to put this mu and nu in the covariant index of G mu nu, and then what will be there? The momentum associated with the photon with which it goes. So, this is something like q square and then plus I epsilon. Okay. And what is this q in this particular case? Q is, you can actually say that this q is P1 minus P3, or you can also have it like this P2 plus q is equal to P4. So this will be P4 minus P2, whatever that you say, and this actually conserves the momentum also, because from here you can see that P1 plus P2 has to be equal to P3 plus P4. So these are all 4 momentum notation that we are writing. So this is what we have. So therefore finally we are now there to write the full matrix element. So therefore what you shall write, that minus of Im as per our definition, this is actually U bar E P3 minus IE gamma mu UE P1 into minus I G mu nu by q square plus I epsilon into this other part, which is U bar mu P4 minus I E gamma nu u mu. Remember that this mu under u is defining the muon, not the Lorentz index. Okay, so this is not the Lorentz index. So this is P2. Now, if you see what happens to this G mu nu when acts on this gamma nu, this makes it gamma mu covariant 1, right. So, therefore, you can simplify or write simply the matrix element in this particular process, that this M is going to what? This minus comes. So, this 1, 2, 3 minus. So, there will be something like, I can bring this minus E square here. The propagator say q square nikal liya. So, minus E square by q square, and then you essentially have u e bar P3 gamma mu u e P1 into u mu bar P4 gamma mu, just because after G mu nu has operated on this, the nu becomes mu covariant index u mu P2. So, if you look into this, this looks like minus E square by q square into some current J mu E into some current J mu. So, this mu is a Lorentz index, and the mu inside the bracket is defining the muon current. So, this is essentially a product of these two current, the electron current and the muon current, with this minus E square by q square, and remember that this q is P1 minus P3. Okay. Now, let us do a very similar exercise, and let us take another process. So, now you can point out that why do I only have to consider electron muon scattering? I can also take a scattering like E plus tau plus going to E plus tau plus, like a positron and an anti-tau scattering to produce an positron and tau plus. So, this is very similar to this one, but remember that these are all antiparticles. So, once again, let us first draw the basic graph. So, the only thing that you have remember that the initial state electron and tau, these momenta are flowing towards the vertex. However, on the same time, the fermion flow should go to the other direction, so that you basically make sure that these are the positrons. And similarly, for the final state positron and tau, the momentum P3 and P4, these are actually going out, but you know the momentum arrow should actually go to the other direction. So, this is the basic difference between the previous graph and this graph. So, this is what you have. So, now the time is that once again remind yourself that I can club an electron or tau or positron or etc. So, for example, I can always teach these 2 points using the QED rule that we have. So, you remember that I can have a positron scattering or electron scattering legitimized by this QED vertex that we defined. So, I can therefore stitch these 2 points together into one vertex, stitch the tau lines together into another vertex, and have the photon exchanged between these two. So, this is pretty similar to what we had before, but just the thing is that you have all the electrons, and but I cannot once again stitch a positron to a tau plus. I cannot do that. That is not allowed by the QED vertex. Okay. So, and then I have the q momentum which is flowing. I mean, you can take it either from that vertex to this vertex or from this vertex to that vertex, that does not really matter. Now, let us try to write the amplitude for this particular process, right. So, here you remember that whenever you have the initial state antiparticle, initial state antiparticle is defined by what? This will be defined by V E bar P1, right. And once again you have the vertex factor, let us write it plus I e gamma mu, just because I have the positron scattering here, and then the final state positron that is being created, that will be denoted by V e of P3, correct. So, this defines the first part of this graph. So, this part is now encapsulated by this part. Then similarly, let's write this part, and this will be basically given by V E. So, the initial tau and tau plus essentially. So, V tau P, V bar tau P2, I E, once again define a new index nu, this is gamma nu, and then this will be V tau of P4, the final state antiparticle that is actually produced. So, this is there. Now, what will be the propagator? The propagator is essentially the same one minus I, the photon propagator, g mu nu by q square plus I epsilon. So, now you can dress it up, I mean just multiply all of them, and that will be minus Im, and it is pretty easy that you can finally idealize that the matrix element here will also be the same, but it will be minus E square by q square, and then you have the current like V E bar P1 gamma mu V E P3, and then this is the positron current, and then you have the tau current, which will be V tau bar P2 gamma mu V tau P4, right. So, this is how you have the matrix element or the amplitude for this particular process. Let us take the next example. The next example is E plus E minus annihilating to a tau plus tau minus. Now, the first question is that the legitimacy of this process, and you see that initial state you have 2 fermions, final state you have 2 fermions. No problem with the spin conservation, no problem with the charge conservation, because initially also you have a particle and antiparticle, and so does in the final state. Electron number is annihilated by the positron number, so the initial electron number is 0. So, there is no restriction that I finally have to have a electron number in the final state. So, tau plus tau minus is perfectly all right. Once again, how to do this? I am going to draw the rough graph using this unknown vertex, and then I will stitch it following my QED dictionary. So, I have the external legs, like you have first the positron with a momentum P2, say for example, where the momentum is flowing toward the vertex, but the fermion flow is going out of the vertex. And then you have the initial state electron, which both the momentum and the fermion flow is towards the vertex with a momentum P1, say for example. Then you have outgoing tau plus with a momentum P4, the momentum is going out of the vertex, fermion flow is towards the vertex, and you have the final tau minus, which is having a momentum P3 going out of the vertex, and the fermion flow is actually along the same direction. Now, the question is, how do I stitch this graph using the QED Feynman rule, right? So, you once again remind yourself that you are only allowed to have electron current. So, here for example, I have the positron here, electron here, and you see this nicely, this can be a fermionic current, and these 2 points, this electron and positron lines, can be stitched together with the photon. So, therefore, what you can do, that you can stitch those 2 points with a photon, and similarly you can stitch the final state tau plus tau minus to another vertex to have the photon. So, you see this photon is now carrying this interaction in a different way. So, in all these graphs that we are doing, that we are thinking that the time arrow is actually along the what you call on the right hand side. So, this is sort of the initial state that I actually have. So, these are the initial state that I have, these are the final state that I actually have, and I am basically trying to construct these graphs using the QED vertex that I know for. So, once again I have all the ingredients ready and I know all the Feynman rules. So, I can write the matrix element. So, first of all, tell me how to write this initial state, this thing. So, you have a initial state positron that will be defined by V bar E P2, and then the vertex factor minus I E gamma mu, and then initial state electron or annihilating electron will be U E P1. So, this essentially defines this part of the graph. So, this is defined by this guy. Similarly, what happens to this part of the graph? You can actually tell together with me while I am writing. So, this part will be given by, so you have basically a final state particle that will be given by u tau bar p3, then you have minus I e gamma nu, introduce another Lorentz index for that gamma vertex, and then you have the final state antiparticle which will be defined by v tau p4, right. So, this is the definition of this particular one, and then we all know how this propagator will be written. This is a photon propagator. So, the photon is carrying this interaction between these two vertex. So, this will be once again minus I g mu nu by q square, and where now you see that this q for this particular case, if this is the q for this particular process, what will be the q? The q is simply P1 plus P2 and which is equal to P3 plus P4. So, this is an interesting point to note that this kind of graph, it is a different looking, right. I mean the geometry is a different one. I will come back to this point in a moment. So, then if you stitch them together, then the minus Im will be V e bar P2 I e gamma mu u e P1 minus I g mu nu by q square with u tau bar P3 I e gamma nu v tau of P4, and so therefore, the matrix element M that will be essentially minus E square by q square V e bar P2 gamma mu u e P1 into u bar tau P3 gamma mu v tau P4, which is simply minus E square by q square j mu e into j mu tau. However, this j mu e will involve this V e bar P2 gamma mu e u e, and this j mu tau will be essentially this guy u tau bar P3 gamma mu v tau, right. Now, there is one interesting point that I would like to mention before I move further, which is that this kind of graphs actually takes a shape like so this graph was actually looking like this one. This is how it looks like, whereas these graphs that we did, this actually looks like this one. So, it is like the propagator, the way that the internal line that connects the graph actually is not exactly the same in these two cases, right, and they have a interesting name. So, this kind of graphs are called S channel graphs. Now, why this is called S channel graph? This is because there is a Mandelstam variable which you can call S, which is simply P1 plus P2 whole square, or this is actually P3 plus P4 whole square. So, therefore, you can see that this q square in this particular way, the propagator momentum that is actually sitting, it is actually giving you that it is telling you that this graph is nothing but minus E square by S into j mu e into j mu tau, right. So, the propagator is actually carrying the information like what kind of interaction or what kind of graph this is actually is. Whereas, here in both E plus tau plus going to E plus tau plus and E minus mu minus going to E minus mu minus, the graphs actually look like this, and the propagator here q, which carries a momentum P1 minus P3. Now, you can define a Mandelstam variable which is t, which is P1 minus P3 whole square, which is equal to P4 minus P2 whole square. So, therefore, you see here in this amplitude, your propagator, the q square, is essentially being shown up in the matrix element like minus E square by t into j mu e into j mu mu. Okay. So, similarly here in this case, if you see this graph also, because the q is essentially P1 minus P3. So it's P1 minus P3 or P4 minus P2. So this is P2 and this is P4. So this Q is always P1 minus P3. So therefore, here also you can see in the matrix element that this will be minus E square by T into the currents that you actually have here, right. So these are the two different kinds of Feynman graphs that we can compute. Lastly, I would like to show you that there is another kind of graph that you can compute. Now we have seen an example where the photon is mediating the interaction, right, but we can have the photon in the initial state, and this is one example where you can have gamma plus electron giving you gamma plus electron, and this is actually a Compton scattering. Once again, it's a legitimate scattering because the electron number is conserved, the spin charges are conserved, you have one photon in the initial state, one photon in the final state. Once again, the idea is that you should first draw the skeleton using a vertex which is like drawn by a blob, and just draw the external lines of the processes using the Feynman rules dictionary that we actually made. Now the point is, how do I stitch these external lines using the QED graphs? So you remember the photon can be connected to an electron, etc. So for example, here you see that you have an electron which is actually coming out. So therefore, the only way that you can stitch it is to draw an internal electron line, and then actually this graphs looks all right. So you have an electron here, you have an electron here with momentum P1, and this is your photon which is going out, this is your photon which is coming in. So this is one way of drawing this graph. But the point is this the only one that I can do? I can also connect this gamma and electron in this vertex also, right? I can actually stitch them there. The only thing that I have to do another electron line, because once again you recall that I have a graph which essentially looks like this. This is what QED actually have told me, that this is the kind of interaction diagram that you can draw. So I can actually have a interline fermionic line joining in this direction also. So these are the two possibilities now in this particular diagram. And now, without doing any calculation, you can imagine or you can tell that this graph is essentially a T channel graph, whereas this graph is an S channel graph, because you know the propagator momentum will be P1 plus P2 in this particular graph, in this one, and this will be P1 minus P3 or whatever that you want to say in this T channel one. So if you write the matrix element, you have to take care of the first graph. You have an initial state photon, so that will be given by epsilon mu P2 if you want to have the Lorentz index mu associated with this one, and this vertex will therefore have a IE gamma mu factor, and then you have the fermionic propagator which is IQ slash plus ME divided by Q square minus M square, and then you have this vertex which will be IE gamma nu with nu as a Lorentz index, and that Lorentz index should also be associated with the final state photon that will be given by epsilon nu star. And this is exactly replicated in the second graph also. The only difference is actually in the Q of the propagator. Like in the first graph, the Q will be actually from this definition, this is actually P1 minus P4, and in this graph, this is P1 plus P2, and the total matrix element will be M1 plus M2. Okay, and here the antisymmetrization rule doesn't apply because this doesn't involve two fermions, or you cannot, any of the prescriptions that we say for which there is a relative sign is under question, that is not applicable. Now why do I have these two amplitudes added together to give you the total matrix element? Because in quantum theory we know that whatever the different ways that you can actually go from initial state to one final state, all those will contribute to this particular process, and these are the processes in this particular case. We couldn't draw any other processes, for example, for E plus E minus to tau plus tau minus. There is no legitimate way of drawing it at the tree level. There are something like quantum corrections, which we do not want to go in right now, but I will tell you more about that later. But for the time being, so this is a beautiful tool which helps us actually to construct and find out the amplitude for all the processes. But remember that while we do the differential cross section, which will give me me actually the number of events that you produce in these processes that will involve a matrix element square. So therefore, we have to learn how to do this matrix element square, and that is what we are going to learn in the next lecture. So thank you so much and stay tuned.